All right, so before we start drawing our Lewis structures, there's yet another thing that we need to understand, and that's resonance structures. And so resonance structures are basically just a way that we fix our Lewis structures. So our simple Lewis structures aren't good enough to describe some compounds, right? Overall, Lewis structures are relatively simple. The quantum mechanics of atoms and molecules is extremely complex, but our Lewis structures are still really good for most applications. One of the modifications we can do is take into consideration resonance structures when we're thinking about what the difference is between the real life molecule and what we draw on our piece of paper. So let's take a look at NO2 minus, nitrite. If we were to do some experiments on nitrite, we would see that the nitrogen is in the middle and then it's bonded to an oxygen on either end. I'm not going to include any of the lone pairs or anything like that. This is not a complete Lewis structure. What I want to say is that these nitrogen-oxygen bonds, experiments have shown experiments show that these two bonds are the same, right? And that's our real life, right? That's actually what happens in nature. We've done a bunch of experiments. We said, hey, these two bonds are the same strength, they're the same length, they're the same bond. However, when we try to draw our Lewis structure, what we come up is one of two structures, right? So we can draw the Lewis structure like this. And we see that we have a double bond here and a single bond here. Or we can draw the Lewis structure like this, where now we've switched the single and the double bond. Now, if you look at these two Lewis structures, what you're thinking is, oh, I have a single bond in one place and I have a single bond in the other place. And if you think about these Lewis structures, they're both equally good. Forgot to add this formal charge here. Right, they're both equally good. All of these atoms have a filled valence shell, so they have the filled valence electrons, and they have a low formal charge as possible. You can't get the formal charge any lower. So what does the real atom look like? Well, experimentally, we've shown that these two bonds are exactly the same. And so what we do when we draw Lewis structures, whenever we draw equally good Lewis structures, we say that the real one is a hybrid of the two. So then we add this little arrow, and this is a resonance arrow, or sometimes called a resonance hybrid. Not necessarily the arrow, but the two structures would be a resonance hybrid. So what this tells us is that the real life structure is a superposition, or we can think of just as a hybrid of the two resonance structures, right? So in real life, it looks something like this. Where these kind of little dots say that this kind of second bond is in both of these, right? It's delocalized. So these little dots show a partial bond that tell us, oh, this is not, a single bond on one end, a double bond on the other. It's somewhere in between. We don't draw Lewis structures like this. We will always draw them like this. Sometimes we'll draw both resonance structures or maybe even more resonance structures. But as you get more advanced, you can just look at one of these structures and be like, oh, yeah, I know that there's another resonance structure. So in general, we don't draw it like this, because there's a loss of information. These dots don't tell you how much of a partial bond do you have. Do you have, 1.5 bonds, 1 3/4 bond, 1 3/3 bond, that kind of thing. When you have the negative charge on the outside, it doesn't tell you where that formal charge is, right? So We draw it like this and include resonance structures, but we understand that the real structure is a hybrid of all of our resonance structures. And overall, this makes sense, right? Remember that electrons are wave-like, so they're often delocalized, right? It's not like this electron is in one place and it can only be in one bond. It can be in multiple places.